we talked about the ways X-rays are created, and the most common, what accounts for most of the X-ray beam is brims. And it's on a magnitude of about 85% of the X-ray beam, unless, it did come with one caveat, and it accounts for 100% of the X-ray beam if we're talking about X-ray beam where the peak energy is under 69.5 kVp, right? If it's under that, then everything is brims. According to what we want you to know anyway, we do create brims in other energy levels, but the only one that we record is the 69.5. So aside from that, everything else is going to be, I'm sorry, I just said that completely backwards. Let me back that up. All right, so almost everything is brims. Characteristic is at 69.5. I think I said it backwards. 69.5. If we don't get to 69.5, everything is brims. Is that what I said the first time? Ish. Or did I confuse you enough? You have no clue as to what I said. All right, so once we get to about above 69.5, and especially if we get up to 100 kVp, then 15% of our X-ray beam is characteristic, and everything else is brim. So even at higher kVp, we still have primarily brims X-ray creation. So brims occurs whenever we lose kinetic energy. The electrons travel from cathode to anode, and they interact on a very small, thin area on the anode, lose kinetic energy, and we gain an X-ray photon that's equivalent to how much energy is lost, right? So that's basically the speed of the electron. How much speed is lost gives us the energy level of the X-ray photon. And even with that, most of our X-ray beam is going to be very weak, and we'll take a look at that again. Characteristic occurs whenever we eject an inner shell electron and replace it with another electron, and the energy level that comes off of that is equivalent to the binding energy of the electron that left versus the one that takes its place. So the highest energy that we can get off of that is 69. And we just count the 69 kVp characteristic X-ray photon, even though we create them in a lot of different energy levels, right? Then we start talking about the spectrum at the anode, not really the emission spectrum, but we're going to talk about the emission spectrum. We're going to take a look at what affects the spectrum and how changing each one of the things that could affect the spectrum is going to make the spectrum look, okay? Then we'll talk about the different energy levels represented on the spectrum and the things about the spectrum that you need to know. So we're going to start with this. We're going to take a look at KVP. We talked about KVP and what happens with KVP, or what happens with our X-ray beam as we change KVP a little bit. On Wednesday, we're going to take a look at mass. We're going to take a look at filtration. I'm going to spend a lot of time on filtration. Machine phase, which we talked a little bit about. And it's not really well represented in chapter 9, right? But they do talk about it in chapter 8. So machine phase, and we're going to talk about SID and the things to look for in questions on SID. So between 8 and 9, what we get to is in 8 is primarily going to be talking about emission, and then in chapter 9 it makes a switch and it goes through all these things again, but it talks about the characteristics of the X-ray beam and its intensity as we go through all that. So we're going to really kind of mesh those two together. Well, while we did that to a degree in chapter 8, chapter 9, we're really going to mash them up, okay? So we talked about the spectrum at the point of impact on the target, and what we had was, if we could draw it out on a graph, and we put on our horizontal axis, we put the energy level as measured in kVp, and then this over here was just quantity being numbers of X-rays that we create. And at the face of the target, what our brim spectrum would look like was that. If we had a characteristic spectrum, it was always going to be in one place, on the energy axis, and that was going to be a 69.5. So if you saw that little spike, that little on the brim spectrum, that was representative of only one thing and only one energy of that one thing. That would be characteristic energy at 69.5. So if you don't have that, what that means is your peak energy is below that, right? If you do have it, that means it's above it. So if you're looking at two different, well, we'll get there here in a bit, but if you're looking at two different spectra and one has one and one does not have one, then what can you determine about those two individual spectra? One's above 69, one's below, right? So you can determine which one, even if you don't see this or this, just the presence of that tells you which one of the two is higher energy. All right, so we kind of drew this out for each one of these with the exception of filtration, so we're going to start with filtration today. All right, so law requires that if you're going to operate an X-ray unit above 70 kVp, you need a minimum of 2.5 millimeters of aluminum equivalent. Okay, and a lot tied up in that equivalent. It doesn't necessarily have to have 2.5 millimeters of aluminum, but it has to have the absorption characteristics of 2.5 millimeters of aluminum. The X-ray beam that you expose the patient to has to go through enough material that it would equal to 2.5 millimeters of aluminum if you were just shooting directly from the target. So, you know, if you had a metal envelope and it was thick enough metal and dense enough metal that it was the same as 2.5 millimeters of aluminum, you're golden, right? You're not gonna have that though. So when we make the X-rays, we accelerate the electrons across the tube and they smack into the anode. They bounce off of the anode and we call equal intensity in all different directions. Our emission is? Isotropic. Very good, isotropic. It's isotropic emissions. But what we want to do is we want to limit the X-ray beam to the useful beam or the useful X-rays that are coming through the window. Okay, so the window is actually in the tube, the protective housing. But what is the X-ray tube itself? What are the components, the internal components of the X-ray tube held in place, or I don't know, maybe not held in place by, but what surrounds them? Glass envelope. It's a glass envelope, right? So you got the glass envelope, and let's see, I'll go this way. The glass envelope. So different types of material, different levels of radiopacity, right? So we've got radiolucency, but we don't have radioapparency, right? So the glass envelope is going to absorb something. It's got to go through the glass envelope and it's going to absorb something, right? So even though it doesn't absorb a whole lot, glass doesn't absorb just a tremendous amount of X-rays, it does absorb some, okay? So back over here to this, if it absorbs some, is it going to absorb, let's go ahead and say that we've got a higher energy X-ray beam. Is it going to absorb these? Likely? No, probably not. What about down here? Most likely. These are very low energy X-ray photons, so at any energy level, we're going to have something that gets so low in energy that we're not even going to consider it kVp, right? So it's going to absorb something. It's going to absorb a little bit of that. So what that means is that our minimum energy increased to above zero. So now our X-ray beam that is emitted from actually the X-ray tube looks kind of like that. Okay, so our peak energy is unaffected. Our minimum energy increased. Now let's walk through an analogy. Let's say I give you 10 tests in a semester. You don't show up for one. All right, you don't show up for one, you don't make it up. What do you get on that test? Goose egg, right? What does that do to your average? You're in trouble for the semester, right? So then, understand this is never going to happen. What if I had a policy to say that I would always throw out your lowest test grade? What would happen to your average then? back up, right? So, because I would throw out the zero. So your average would go up. I'm never throwing out the lowest test grade, so don't get your hopes up there. I'm just using it as an analogy. So, if I have energy levels that go from 0 to, I don't know, just give it a number, we'll say 80 kVp, before the X-ray beam goes through the glass, just in a word, because we go from 0 and a lot of 0 kVp up to 80 kVp, which is very few, what is your average beam energy in a word? High? Well, how many 80 kVps did you get? You got them, but almost none. How many 0 kVps did you have? Here? If this is all numbers, a lot. You had a lot. So your average is very, very low before the filtration. But with the filtration, you eliminated the zeros, so now your minimum beam energy may be 5. Did it increase your average? Yeah, it did. But in a word, what is your average still? Pretty pathetic, right? So then what does it got to go through? Okay, so protective housing is out here. Okay?
Oil.
Bingo, the oil. What are the characteristics of oil? Kind of similar to what? I'm just going to sit over here and drink this liquid while you think on it. Well, it's similar to water, right? It's lighter than water, but it's similar to. What are you made of? Water and basically grease. I mean, we're fat, right? You ever brown hamburger meat? What do you get off of it? Oil, right? Grease. So is that going to absorb some X-rays?
Mm-hmm.
Yeah. All right. So then if the glass envelope eliminated some, can you kind of see how that would as well? So now your minimum is a little bit higher. And what happened to your average? It went up. Right. So then what does it go through? And that oil just suspended in air, right? It's not held in place by anything. Right? No. I just got to look. So, don't be stupid. No, it's held in place by something, right? So it's got to go through the window. The window's probably, again, some sort of either glass or metal, something. So what that's going to do is it's going to take some more of those low energy photons and get rid of them. I need to tilt that a little bit more. It's going to get rid of some more of those low energy photons. And so our average goes up. The minimum energy, the energy level of the minimum energy also increases. So maybe now our minimum kVp is, let's just go with 8. Okay? So it goes through the window. You got this box hanging down from the bottom of your protective housing. That's your collimator housing, right? So at collimator housing, you've actually got 2 sets of collimators, and we'll talk about that next semester. Amy may have talked about it already. But you got 2 sets of collimators, and that's just beam restriction. Doesn't do anything except for restrict the beam. But how does your light work? Have you ever looked up inside of your collimator housing?
No.
Seen that light bulb?
No.
No, you can't see the light bulb because the light bulb is not directly inside the collimator housing. It's off to the side over here so that whenever you make an exposure, your X-ray beam is not filtered by your light bulb itself, but in order to project that light directly down so that we can, use it to position a patient, what does it have to bounce off of?
Mirror.
It's a mirror, right? So what's on the back of a mirror that makes it shiny? Stuff, right? Maybe some sort of metal foil of some sort. It used to be silver. I don't know that they do that anymore, but it's some sort of metallic stuff, right? So it goes through the mirror, and what happens is you get a little bit more absorption and your average goes up. Okay, so filtration does all that stuff. Now, if all of that, going through this, and this gets us to 2.5 millimeters of aluminum equivalent, then we don't have to have any more filtration. If your oil isn't, the thickness of your oil isn't enough that it would get it to that, then you would have to add some filtration to that in order to get it to 2.5 millimeters of aluminum minimum. Every X-ray tube that you use, be it portable, be it C-arm, be it stationary, whatever, has a minimum of 2.5 millimeters of aluminum, okay? Brand new X-ray tube is always gonna have, any one that you ever work with is gonna have minimum 2.5 millimeters of aluminum. That's law. You can't make an exposure on a patient unless you have that, okay? So let's do this real quick before we go any further. You have two different types of filtration: inherent and added. All right, so some of your textbooks, you may read some different things about inherent and added filtration. I'm going to tell you what we're going to consider inherent and what we're going to consider added. Okay, so some textbooks will say, well, the only true inherent filtration is that's on the envelope. And by the strictest definition, that's true. Can you take the X-ray tube out of the protective housing and create an X-ray? Can you do it? Now, I'm not saying strictly should you do it. I'm saying, can it be done? Yes. The answer is yeah. Yeah, absolutely you can. You can connect that directly to some high voltage source and you can create X-rays that way. Do you want to be in that room? No. Do you want somebody exposing somebody you love to an X-ray being created that way? Again, the answer is no, you don't. So that 2.5 millimeters of aluminum being required by law is what we're going to call inherent filtration. It's what you have to legally make an X-ray, okay? So our inherent, for our purposes, inherent filtration is going to be everything that gets us up to 2.5 millimeters of aluminum. So what if all of this brings us to 2.0 millimeters of aluminum? Can we legally make an X-ray and expose a human being to that X-ray beam? The answer is no. So what we're going to do is, before we get to the mirror and the projected light, we're going to put an additional 0.5 millimeters of aluminum to bring us up to 2.5 millimeters of aluminum. Okay? Now, is that added filtration?
Yeah, but it only gets us to the 2.5. So
Right, so we can't legally shoot it until we add that, so that is still inherent filtration for our purposes. Okay? Anything that gets us to 2.5 millimeters of aluminum is inherent filtration. It said that you might see some different things in different textbooks. So some of your textbooks may say just envelope. Some of your textbooks may say, everything, including the mirror, but not anything above that, right? And we're going to say that 2.5, and first off, if you run into different things in different textbooks that are not online, but like Carlton versus Bushong, chances are you're not going to see it on registry, okay? If there's something that's I won't say debated, but there's a lot of difference of opinion, you're probably not going to see the question on the registry that specific. So for our purposes, that's what we're going to call inherent filtration. Anything that's added above that is what we call added filtration. So the definition of inherent filtration is something that is what you cannot remove from the imaging system. You can't do it. You can't scrape out the tube. You can't do anything. Okay? So it's going to come to you with 2.5 millimeters of aluminum. Okay? But what happens as the tube ages and it eventually leads potentially to arcing? What do we call that process? Tanning. Exactly. Tanning. All right, so tanning is going to add filtration. As the tube ages, you're going to get that layer of tanning, which is going to increase the filtration. That is still inherent filtration. But wait a minute, it's above 2.5 millimeters of aluminum. Yes, but remember, it's 2.5 millimeters of aluminum, and that's minimum, right? That's the floor, that's not the ceiling. You can add as much as you want to, right? So you got 2.5 millimeters of aluminum, but as the tube ages, that increases. Okay, so why do we still call that inherent filtration? Because you can't remove it. You can't take it away, right? So could you go back, if you got 0.5 millimeters of aluminum equivalent in the tanning, could you go in and remove that? Yeah, you can. It's never going to happen, but you could, theoretically, right? So 2.5, the few things about inherent filtration, 2.5 millimeters of aluminum. Doesn't all have to be aluminum. It's whatever the beam passes through that would equate to 2.5 millimeters of aluminum. Have to have it. It's your inherent filtration. Have to have it. Brand new tube, probably just coming right in at 2.5 millimeters of aluminum. That increases with tube age because of tanning, right? So let's, everything about inherent filtration. Added filtration will be anything that brings us above that 2.5 millimeters of aluminum that is not tanning, okay? And in the added filtration, what we have is just straight up, filters in the same sense as what adding more filtration here would be, okay? So why would we ever want to increase above 2.5 millimeters of aluminum? You're probably never going to do it, right? But possibly something like a mammo application, which you're not going to shoot mammo with your diagnostic x-ray tubes. They've got specific tubes for mammography. Possibly if you were doing, probably not see it, but possibly if you're doing pediatric patients, you would want an x-ray beam that, had fewer low energy x-ray photons. So those sort of things. So you got that, but you've also got added filtration, which are compensating filters. Okay, so compensating filters, you don't see those a whole lot anymore because our computer algorithms even out the appearance of tissue densities pretty well. Where we used to use compensating filters quite a bit was pretty much, in some cases, pretty much the same as where we would use anode Hill effect, okay? So if you got something like a foot, foot being we're not gonna have a blocky foot today, we're gonna have a wedge-shaped foot. But if we had a foot, we're thicker here than what we are here, right? So when we shot feet with screens and films, what you had to do was set a technique for where the patient's pain was. Okay, so you ask the patient what happened to you. Where do you hurt most? If they say it's on my foot, but it's closer to my toes, we would have to select a totally different technique than if they dropped it across, your forefoot, the thickest part of the foot. Okay, because if you shot for this, you'd burn those out. If you shot for that, that'd be too light. Okay, so we had to select a technique based on where the patient's pain was. Or we could use a filter where we would take the filter and put the filter on the collimator housing, and it just had this slot that you would slide these things into, and it was a chunk of aluminum. And what we would do is take this chunk of aluminum that was mounted to a plate and slide it into the collimator housing, and we would put the thick end of the compensating filter over the toes, thin end over the foot, so that by the time the x-ray beam came through this, then we had a lower intensity on the toe end and a higher intensity on the foot end. It would even out those tissue density differences. Okay, so still testable. You're probably never going to see a filter in clinicals, any of your clinical sites, unless it's just on display, but it's still testable. So compensating filters compensate for tissue density differences, kind of in the same way that you would use an anode Hill effect to do the same thing. Okay. What you might see is it's a type of compensating filter, but not exactly, and that's what you call a trough filter. A trough filter is kind of like a wedge filter, but it's on two sides. Okay. So So what a trough filter is a filter, and where we use trough filters most of the time is in scoliosis series. And it's where this wedge filter was big, the trough filter was is two small filters that run, if I was shooting a chest x-ray, then the trough filter would be oriented so that the filters were running up and down, okay? And the purpose for the trough filter is to avoid, or to, not avoid, but to provide extra layer of beam absorption and protection on scoliosis series. So you collimate down, you get the patient position, you collimate down, and you put this trough filter again into your collimator housing, and we take our scoliosis series. So we talk about spines kind of at the end of the semester, and we always shot scoliosis series PA, or we would prefer to, right, for radiation protection, because most of our scoliosis patients are going to be young women, right, girls. Developing breasts, we want to protect those, so that's what the trough filter is all about. So if you're ever in some clinic doing scoliosis series and you see them slide that thing in, that's what it is. It's not really a compensating filter. It's an extra layer of radiation absorption to try to protect and lower the breast dose. Okay. Other types of compensating filters are boomerang filters, or another type, and that would be something that you would lay under the patient's shoulder, because in shoulders, in a lot of cases, what we would get on screens and films, again, is too much darkness of the image or density on the lateral portion of the shoulder. Okay, so those are all examples of compensating filters. And really the trough filter doesn't really compensate, but we still consider it a compensating filter. Okay, so added filtration is anything above 2.5 millimeters of aluminum, regardless of whether it truly filters or if it's just beam restriction. Fundamentally, is still considered the same thing. Okay, so most common two types of compensating filters would be a wedge filter and a trough filter. Okay, so in each one of those cases, though, the same thing happens to the energy of our X-ray beam. We move where we start creating the X-ray, so our minimum X-rays increase. These are all going to be absorbed inside of the patient anyway, right? Just adding to patient dose. There's no chance that a 1 kVp X-ray photon is going to make it through a patient. Get rid of it, right? So we get rid of those low energy photons, we keep the high energy photons, and what that gives us is a beam it's not homogeneous, but it's more homogeneous. Homogeneous means same, right? So it makes it more homogeneous, and it puts it more in the same energy range, even though we've still got a considerable energy range, right? So now we're at 10 to 80 kVp energy range. So the things that we can see on the brim spectrum are minimum energy, right? So what controls our minimum energy? Only one thing. Filtration. It's the only thing it controls. It's the only thing filtration controls is minimum energy, and the only thing that controls minimum energy is filtration. Okay? All right, so that's what filtration controls. So that's minimum energy. We can tell maximum energy if it's marked. If it's not, then we can tell it's above 69 kVp if it's got that spike, right? So what controls our peak energy? kVp, right? All right, so we'll take a look at that here in a minute. But what falls in between is the peak of this bubble, okay? This represents numbers, and this represents average, okay? So with filtration, what we did was we increased the energy level of the lowest energy X-ray photons, and we moved the average towards the high energy side. So if we added any more filtration, what we would see is this. So our average now is here. Okay? So here's the problem that you're going to have, you know, understanding technique and filtration. Okay, so as we added filtration, what we got is a X-ray beam that is average, it has a higher average energy, right? So now our average energy on 80 kVp, let's make it easier and go with 90, because our average is right about 1/3, which means that before we added this other filtration, if we had a 90 kVp X-ray beam, our average beam energy was 30, right? 30 kVp. So our average beam energy is 30 kVp. If I added more filtration, what happened to my average? Did it go to the low energy side, or did it go towards the high energy side? Went to the high energy side, right? But what did I lose? What does the area under that curve represent? Numbers. It represents numbers, right? So we lost some numbers. We lost low energy photons and even some of our average energies, right? We lost numbers. So what if we shot our foot and we shot it without a filter and we shot it with a perfect technique, right? So, I don't know, 65 kVp, 2.5 mass, somewhere along in there. We shot it with a perfect technique and then I added filtration. What's going to happen? What's going to happen to the intensity coming through the filter? It's going to be less. We're going to have less photons, less intensity. So what am I going to have to do? Mass. Right, so compensation for loss of photons is always going to, not always, but almost always going to be mass. Why? Well, if I lose 100 photons, let's say I create 200 photons, I'll lose 100 photons, but I need, let's say I need 200 photons, I'll lose 100 photons. How much of a change in my technique, in my mass, do I need to give me those 200 photons? I need 200, I have 100. That's a factor of 2, right? I just increased my mass by a factor of 2. So could I do that with KVP? Yeah, we talked about KVP on Wednesday and that it's an exponential change, right? So I would need how much of a change in KVP to equate the same thing? It'd be 15%. Is it easier to multiply by 2 or to increase by 15%? Multiply by 2 all the time, right? So, and it's for ease, but also we're going to take a look at KVP and look at how it changes everything in the beam here in a minute, okay? So y'all good with filtration? The things to remember about filtration. Inherent, right? Inherent filtration increases because of tanning, right? Still inherent filtration. Added filtration is anything above that, and we've got subcategories of added filtration, just regular filtration. We've got, you know, they can even use copper for filtration. What that would do is drastically change our brim spectrum for filtration. And then we've got compensating filters. Compensating filters compensate for tissue density differences. Okay? So that's all filtration. Pushes, we lose energy, or we lose numbers, pushes all our brim spectrum, the average towards the high energy side. We lose numbers, though. We lose intensity. We have to add back in that intensity. We're going to use mass. Okay? All right, so we drew out the rest of those really as X-ray creation, not emission from the X-ray tube. So considering that we've got to go through all that same stuff with each one of these things, I'm not going to draw, or I'm going to draw it out, but I'm not going to, you know, leave that up on the board. So let's take KVP. The things to remember about KVP is it controls our peak energy, it controls our penetration, It's our potential difference on the X-ray tube. We apply high KVP, we apply a high electric potential. We increase the speed of the electrons as we increase our KVP. Changes the frequency and wavelength, right? So we get a higher frequency, a shorter wavelength with increased KVP. So if we have an X-ray beam that we shoot at 60 KVP, and it looks like that at the face of the target, then we know that it's below 69 KVP because it has no characteristic spike. If I change my kilovoltage and I go to, again, 90 KVP, then I'm going to increase the peak energy. There's only one thing that's going to increase the peak energy, right? There's only one thing that changes the minimum energy, that's filtration. The only thing that changes peak energy is KVP, nothing else, okay? So once it goes through all those levels of filtration that we talked about before, our KVP, our brim spectrum is going to look like that at 60 KVP, right? So we've still got a lot of low energy photons. Our peak energy is 60. Our average energy is around 1/3, so our average is going to be about 20. And our numbers created are, you know, they are what they are, right? But as we increase to 90 KVP, what's going to happen with our average? Going to increase, right? So our average now is going to be around 30 KVP, right? Same levels of filtration. So at the low energy, our filtration, our effects of filtration are going to be about the same, but look what happened. We don't stop making any of the X-ray photons that we created before, we just added more on, and especially at the peak energy. So what happened to our average? It increased, right? So our average now is at 30 KVP, and it pushed our average towards the high energy side, right? But look what happened to numbers. What happened to numbers?
Decreased.
Decreased? Did you say decreased? Yeah. No, we're over here. They increased a lot, right? A 15% increase in KVP equates to how much of a change in mass? Double, right? Remember toilet paper math, right? That's where this applies. 15% increase in KVP is so significant, it gives you the same, at least at the image receptor, the same effect as a doubling of the mass. So KVP changes everything. So KVP, again, potential difference, speed of the electrons, electric potential. What does it control in the patient? It's still another P word. Penetration, exactly, controls your penetration. So what we get with a higher KVP is we get more penetration on the high energy side. 30 KVP going to penetrate better than 20 KVP? Yeah, so we get more penetration all the way across the beam. So it changes the imaging characteristics of the beam. It changes everything about the beam, right? As a result, we don't want to use KVP as our go-to change in technique. There's times we need to, but that should not be the first thing that we think of when adjusting technique. If we need an increase in penetration, it's getting kind of into next semester, but if we need an increase in image receptor exposure and an increase in penetration, this is our technique. But it changes both of those, right? If we need an increase, let's say an increase in image receptor exposure, and we don't want to increase the patient's dose quite as much as doubling our mass, this is our exposure factor that we would change, okay? So it changes everything. The unfortunate consequence of increasing KVP is an increase in scatter radiation too. Okay, we'll get into specifics of how that actually works and whether It changes percentage of scatter, and it's real complicated. So we're not going to step into that today, but we'll talk about it next semester. But it changes everything. It changes scatter, it changes penetration, it changes exposure, it changes patient dose, it changes everything. So we don't want to use that. We can, don't want to use it. Times to use it, yes, but most of the time not. All right, so it also determines whether or not we get a characteristic spike. So KVP in the brim spectrum doesn't do anything to the minimum because that's filtration, right? It's the only thing that affects the peak. It increases the numbers dramatically, exponentially, right? It determines whether or not we get a characteristic spike. It pushes our brim spectrum towards a high energy side, so we get a higher average, more numbers, higher peak, KVP. Okay? So then we got to look at mass. All right, so mass, with mass, we've gone through the layers of filtration. We've got a brim spectrum that looks like that. Doesn't really matter what our peak energy is. Our peak energy is controlled here. Minimum energy is controlled here. We're just going to look at numbers. So when you change your mass, what do we refer to mass as? Intensity. All right. Intensity in this context is just numbers. Nothing but numbers. Okay. I struggled with this when I was in school. I wanted to make KVP intensity, you know, because this is high energy. You think of something that's very intense, it's very high energy, but you know, in this context, it's just numbers. Intensity equals numbers. This is the power of the X-ray beam. This is the intensity. Okay, so just lock that away in there. It is what it is. Okay, so as we increase mass, we already determined that that is the only thing that controls peak energy, right? So if we increase the mass, we're still going to intersect that line at exactly the same spot. We already determined that filtration is the only thing that determines the minimum energy, so we're going to intersect that line at the same spot. So the only thing that's going to change is the area under the bubble. Average should remain the same. Again, for simplicity's sake, we'll say we're at 60 kVp, right? So our average here is what? 20. When we changed, let's say we had our mass, our original mass was 20 mass. What you're shooting with 60 kVp and 20 mass, I don't know, but you shouldn't. And we changed to 40 mass. What happened to our peak energy? Nothing. What happened to our minimum energy? Nothing. What happened to our average energy? Nothing. So that only leaves one thing, and that is, what did it increase? Numbers only. Only thing that increases is numbers. So since it doesn't change the imaging characteristic of the X-ray beam in any way, and it's easy to calculate, most of your technique compensation, most of the time, unless you need to change KVP for penetration purposes or radiation safety, you're going to change your mass. Almost every time. Okay? So it just changes intensity, right? Exponential change in intensity, direct exponential, direct. That would be an inverse, you know, as filtration goes up, intensity goes down, right? So let's say machine phase. Machine phase. So you have single phase brim spectrum that looks like that. Okay? So again, only one thing controls the minimum, only one thing controls the maximum. So we're still going to have intersection here, intersection there, in exactly the same spot. And this is what you're going to have a tendency to confuse as machine phase and filtration. When you go from single phase, so we're going to make the green single phase, and we're going to make the blue three phase high frequency. All right. So what happens as we go from single phase to high frequency, and we talked about this on Wednesday, is the peak energy never drops, or the energy of the X-ray beam that we create never drops to zero, right? So we have those overlapping pulses. It never drops completely to zero. So if you eliminate all those zeros before you run it through the filtration, what's naturally going to happen to your average? You drop your lowest test grade and it's going to increase, right? So what we're going to get with three-phase over a single phase is an increase in the average. Okay, the average is going to increase. It's not going to be as dramatic as what it is here, but it's going to be present. We also said on Wednesday that as you change from a single phase to three-phase, what happens to your output? What do you need to do with your technique? Decrease. You need to decrease your technique. If you go from single phase to three-phase, you're going to increase your output, and you're going to need to change your technique accordingly, right? So the change from single phase to three-phase is a factor of 2, right? So what we're going to get is a change in numbers. So what? So our average should have remained in the same spot. It looks like I was a little bit off, but our average should have remained in the same spot on both of those. So if we have a 60 kV, no, scratch that. Because it never drops to zero, our average is going to increase, our numbers increase, our average is going to increase. So if we're at 60 kVp, and these are just arbitrary numbers, it doesn't really matter what the numbers are. It's just for demonstration purposes. For the single phase, if our average beam energy was 20, because we're on 60 kVp, with three phase, it might be 20, just 25. Okay, not as dramatic as kVp, but it's going to be present. Okay, so as we change from single phase to three phase, we get an increase in output. That's increase in numbers, number of X-ray photons that we create, and we're going to push it towards the high energy side. So this is why I say you're going to have a tendency to confuse machine phase and filtration, is because it's not as dramatic as kVp, and it kind of does the same thing, and that is that it changes our average and it changes our numbers. But notice, we go from single phase to three phase, our numbers go up and our average goes up, direct, right? But with filtration, our numbers go down and our average goes up, okay? So our technique correction here is to increase mass, right? Over there, our technique correction would be to decrease mass, okay? So again, that's more imaging for next semester, but just to kind of tie it all together. Now, SID is something a little bit different. I'm going to tell you all the things to look for on a test on SID. So SID, source to image receptor distance. We've discussed the inverse square law. We've discussed the direct square law, technique compensation for those. So I'm not going to go through the math on all that, but I'm going to tell you what to look for. So when we have an increase in SID, our beam, because of the divergence of the central ray, is going to spread out, right? We took a look at that with the flashlight. If we're real close, we get a very concentrated beam, but the further out we go, the more it spreads out. The light doesn't get less intense, right? The characteristics of the light field remains, or the light at the flashlight remains the same. The only thing is that, if I'm shining a light on that little green stripe right there, it's catching more of the light, right? As I get closer, the further out I go, the less it does, right? It spreads out more. Okay, so that's the way the X-ray beam works as well. If we bring the X-ray beam closer to the image receptor, we get a higher intensity at the image receptor in that spot, right? But as we back up, it spreads out, and because it spreads out, we need to collimate. And we're eliminating some of that X-ray beam, right? So we use two laws to describe that. One is the inverse square law. And one is what we call the direct square law, density maintenance formula, or technique compensation. All that kind of means the same thing. But the inverse square law, what you're going to look for on inverse square law in test questions, it may say as you increase your SID, the exposure to the image receptor, could be exposure to the patient, is going to decrease because of inverse square law. Right? Inverse, opposite, square, exponential law never changes, right? Inverse square law. So as you increase your distance, the intensity is going to decrease by a square of the change in distance. So the first thing you're going to have a tendency to do is if you double your distance, what's going to happen to your intensity? Just in a word, it's going to decrease, right? But you doubled your distance, right? So it's going to decrease by a factor of, you're going to want to jump on 2 every time for a while, right? But it's the square law. Mathematically, what's a square? Something times itself. Your change was 2. 2 times 2 is 4, right? So it's going to change by a square of the distance. So you double your distance, the change is going to be a factor of 2 squared, right? So it's inverse. One thing goes up, the other thing goes down. Distance goes up, intensity goes down. Square the distance 2 squared is 4. So your intensity is going to decrease by a factor of 4, and it's going to happen every single time you double your distance. Never going to change, okay? So inverse square law, how you're going to recognize when to use the inverse square law is most of the time it's going to be weird distances. Most of the time, not always, but most of the time it's going to be weird distances. You're standing 2 feet away from a fluoro table and you're receiving X exposure. You increase your distance to 4 feet. What's going to happen to your exposure? It's going to decrease by a factor of 4, right? So that's number one, weird distances, 2 feet, 4 feet, 1 foot, 3 feet, things like that. It's also mostly going to be read in radiation exposure and not mass. Okay, so your exposure, and we're talking about occupational exposure, so it's going to be read in MR if you're using, the people we use. Your MR at 2 feet is X, whatever. You increase to 4 feet, your MR is going to be something else. Okay, so those are going to be your inverse square law exposures. You decrease your distance, what happens to your dose? Goes up by a factor of 4. If the change is a factor of 2. Okay, so those are your trigger points for your inverse square law. Density maintenance, though, is going to be your square law, and it's the same thing. It behaves exactly the same way, but it's technique compensation, right? So because you increase your distance, you decrease the intensity at the image receptor according to the inverse square law. You use the square law to compensate in technique. So these are going to be mass. This is going to be mass questions. You used 10 mass at 40 inches and you increased your distance to 80 inches. What's your new mass? Well, you increase the distance, so you're going to have to do what with mass? Because of the inverse square law, as you increase your distance, you lost intensity. What are you going to have to do? You're going to have to increase it, right? So this is not an inverse relationship. As you increase your distance, you're going to increase your mass. As you decrease your distance, you're going to decrease your mass. But it's going to be by exactly the same amount. So you increase your distance from 40 to 80, then your mass is going to have to go up by a factor of 2 squared, which is 4 every single time because it is a law, right? We also talked about earlier in the semester, we usually don't go 40 to 80, we usually go 40 to 72 inches. What was that compensation for 40 to 72 inches? You remember? 3.24, right. It's mathematically it's 3.24. You're never going to get to a test and have something like, if you have a hard time hanging on to 3.24, just think 3 1/4, right? 3 1/4 will get you there. You're never going to have an answer on a test, even my test. You're not going to have an answer on a test that gives you both of those, 3 1/4 versus 3.24. You're just not going to see it. So, you know, if you're working on something on a test and you know you worked something close to right, but it's that far off of one of the answers, chances are it's rounded or something like that. Okay, so that's going to be mass always, right? This most of the time is going to be some measurement of radiation exposure. Weird distances you're more accustomed to seeing, making your exposure. So the other things to look for is this doesn't affect the BRIM spectrum at all, right? BRIM spectrum is emission from the X-ray tube. So if you're doing this is something else that you need to look for, is if you're doing a portable, let's say, and you make an exposure, it's perfect exposure today at 40 inches, you know, patient can't sit up. You come back and you're, the patient, you know, they're miraculously healed and they can sit up and you back up to 72 inches, you use the same technique. What is going to be the result?
Underexposed.
Underexposed, right. So your your index number is going to indicate that you've underexposed the patient. Even if your image looks good, it's still going to be underexposed, right? Is that because you had a difference in output from the X-ray tube?
No.
The answer is no. Right, so you're going to see questions that ask, as you increase your distance, what happens to the output from the X-ray tube? Nothing. Except, now we're tying stuff together from earlier in the semester, how do phototimers work?
Penetration.
What's that?
Penetration. What I said.
Penetration, right? So they're going to count X-ray photons coming through the patient, right? So as you back up, you increase your SID, you back up your X-ray tube, what's going to be the result of the interaction on those phototimers or the AECs?
Longer time.
Okay, very good. More time, right? It's gonna, you know, your timer is gonna have to run a little bit longer to compensate for that, right? Now, is that gonna change the emission from your X-ray tube?
Yes.
Yes. Why? Because that's seconds. Your mass went up, right? So look for those things in distance. Know when to work the inverse square law. And you know, here's a dirty little secret. We're going to throw all kinds of distances at you over the next 2 years, right? When you get to the registry, you should be able to work these in your mind. You really should, you know, because they're going to be pretty close to double or half, or 72 to 30, 72 to 40, 40 to 72, those sort of things. You should be able to work those. There's very little on the registry you should, if we beat it into you enough, that you should have to use calculator for. Okay? So look for these things: radiation dose, mass, right? Don't forget to square it, because you're going to have a tendency to want to jump on double distance, double technique, and it's always going to be a factor of 4 if you get a double, you know. Or you're going to have a tendency to go in the wrong direction with it, which means that, you know, you're going to increase your SID and you're going to decrease your mass. Okay, you got to increase the mass. You'll have that. You know, if I give you a scenario where you've increased your SID, I'll give you the answer for if you go in the wrong direction. Okay, so make sure you're going in the right direction with it. Mass, output from the X-ray tube doesn't change unless you either change your mass or your phototiming. If your phototiming is the machine is going to increase the mass all by itself. Okay, so all that is about radiation exposure at the image receptor. Okay, what you create in the X-ray tube, and that's why we jump into that in the very first lecture, that kind of intro this semester, is that you got to, and that's why we start the curriculum with this class, because everything else builds off of this. You can't really fully understand imaging in image creation or radiobiology and what's happening inside of the patient unless you understand what it is that you're doing inside of the x-ray tube that affects all this stuff, right? So hopefully this will help you with radiation protection next semester, especially where we have changes in KVP and how that changes interaction inside of the patient, and how we can minimize patient exposure. As you increase KVP and decrease mass, patient exposure goes down. Imaging characteristic of the beam changes quite a bit too, but you can't really understand all that stuff until you understand this stuff, right? So you understand this stuff and it makes that stuff easier. I'm not saying it's going to make it easy, but it makes it a little bit easier, okay? Any questions? What you got?
The filtration and KVP, doesn't that, the filtration still change the KVP over here?
It doesn't control the peak. Okay, so what I gave you here, yeah, I just kept it safe. It changes the average, so you're going to have a tendency to imagine the average as equaling the peak, right? So and even in the question, sometimes it'll say it changes the average KVP of the X-ray beam. It doesn't really change the average KVP. P refers to the peak. That's the highest energy that you're going to create. And that's just based on loss of energy, loss of kinetic energy in the target. So it doesn't change the peak energy, but it does change the average energy so that it's on average a higher, better penetrating X-ray beam. Okay? Is that kind of...
Yeah, I get it.
Okay. Okay. I almost forgot about this, but I want to touch on this before we leave. So KVP is what we use to as our measure of beam quality. Okay, so KVP is beam quality. And that's because if we made an X-ray beam that was all low energy, didn't penetrate through the patient, we couldn't create an X-ray image, right? So we have to have penetration. KVP controls penetration. Penetration equals quality, okay? So KVP equals quality, but it's not the best measure of quality. It's a measure of quality. It's the easiest measure of quality, but really the best measure of quality is what we call half value labor. And we touched on this early in the semester whenever we talked about radioactive half-life. So some of y'all, you may be ringing a little bit of a bell, but and hopefully this will remind some of y'all. All right, so half-life. If we have two X-ray tubes, so we got one X-ray tube, we've got two X-ray tubes, both of them, let's say, are making an exposure of, I don't know, 75 kVp. KVP really doesn't matter in this case, 75 kVp, and we are making an exposure of 10 mass, and that gives us 50 milliroentgens. What would that be? 0.5 gray? What? It doesn't matter. Just a number. Okay. So I got X-ray beam over here, and I got X-ray beam over here. Two different rooms. This one is brand new, just installed yesterday. What's your filtration? 2.5 millimeters of aluminum. 2.5 millimeters of aluminum. Okay? So what happens as tube ages? You get tanning, right? So with tanning, because it's the type of filtration, we lose numbers. Every year, your biomed guy has to come in, he has to make adjustments in your tube to make sure that your output measured in radiation exposure in air, gray in air, or milliroentgens, remains the same. Okay? So you're going to lose numbers every year that you use a single X-ray tube. And they're going to have to come in, they're going to have to tweak it to get it back to the same radiation exposure. But what's happening as the tube ages? Let's say year one, they come in and our radiation output is down from that to 5 below that. What are they going to have to do? They're going to have to up it until it's at 50 again. But what's happening to the characteristics of our X-ray beam? More filtration, right? And the more filtration moves our average towards the high energy side. Okay, so the high energy side pushes it more towards KVP. And what does the KVP control? Penetration, right? So as the tube ages, our X-ray beam becomes, as they change it up, it becomes more penetrating, okay? So half value layer takes that into consideration. So we've got, I'm not even gonna put, let's say that's 5 years old. It's got tanning, right? So we put an absorber, some sort of absorber, probably aluminum. Let's say it's 1 millimeter of aluminum. Again, these are just numbers, just to make it easy. So we make an exposure on this. We started out with 50 MR on tube A, and we make an exposure of 50 MRs right here. Coming through that, we cut that down with that 1 millimeter of aluminum and cut it down to 25 MR, okay? Half value layer means the amount of an absorber it takes to cut the intensity of the X-ray beam in half. Did we accomplish that here?
Yes.
Yeah, we did. So the half value layer of tube A is 1 millimeter of aluminum. So we use the exact same millimeter of aluminum over here when we make the exposure. We've got 50 MA right there, or MR right there. But below this, we've got, instead of 25, we've got 35. So what are the imaging characteristics of this X-ray beam versus this one? Did one penetrate more than the other? Which one penetrated more? B, right? Well, what about penetration? What do you know about penetration? It's KVP, but what does KVP control? Is our beam quantity or quality? Quantity, yes, but quality is what we want to focus on at this point, right? It controls our beam quality, right? So if penetration equals quality, quality equals KVP, which one of these is better? That one, right? So if we add a second one, and it drops it to 25. So we've got now 1 millimeter and another millimeter of aluminum, and it takes 2 millimeters of aluminum to get to half of its original intensity. We can say the half value layer of beam B is 2 millimeters of aluminum. Half value layer of beam A is 1 millimeter of aluminum, right? So higher quality X-ray beam. Okay, so it's a better measure. They're both 75 KVP, but this one penetrates more. Okay, now some of y'all are going to say, well, then why is tanning bad? Well, you get to arcing, right? Well, why don't we just add more filtration? You get to a point of diminishing returns. And what that means is that you can add stuff to the point that, you know, you're just adding stuff to add stuff, you know. Think of it as painting a room. Anybody ever paint a room? How many coats you put on a wall? A couple, right? All you want to do is cover the stuff, the old paint that was there, right? Do you put tin on it? Would tin be better? Not really. You're just wasting your time. You're wasting money, right? So you can put too much filtration, and that's a bad example exactly, but you can put too much filtration. All you need is 2.5 millimeters of aluminum to get to an adequate amount of filtration. So we don't go above that to get to this point. It just does it on its own because it's tanning. Okay. So half value layer, KVP is a measure of beam quality. Half value layer is a better measure of beam quality. Just file that away. You're never going to actually work it. You'll work a problem for this, but you're never, in clinical practice, you're never going to, measure that. Okay. But I almost guarantee it'll be on registry. All right. Now, any questions? Any questions on the review? Anybody had an opportunity to? Yeah. What you got?
I didn't ask this last time, but I'm still confused. The induction motor.
Mm-hmm.
On the review, said it's on the outside.
Yeah. It's on the outside of the X-ray tube.
Is that the stator?
Yes. Yes.
Okay.
It's an electromagnet, induction motor, stator, homing center. Yep.
Even the book it says it's both the stator and the rotor, so I was confused. I think,
It says the induction motor is?
yeah. I don't know.
Yeah. Yeah, the stator, maybe the whole thing as being the anode. I don't know. I'd have to take a look at it. But the induction motor itself is just the electromagnet. It's inside of the tube housing, outside of the envelope. Okay.
And then I have one more question about,
Yeah.
I was confused about characteristic radiation. Can you want to bring that up?
Characteristic? Yeah. Characteristic, so you got BREMS, right?
Yeah.
Okay. Characteristic radiation occurs when you eject, and again, the only one that we're really going to concern ourselves with is the inner shell. It happens at every shell. And it, like Bushong says, the only one that's any, of any consequence is the K shell. And I disagree with that too, because, well, okay. I don't disagree that K shell is the only one. I disagree that 69.5 is the only one of consequence, because our average beam energy is quite low, right? So anyway, we eject an inner shell electron. The electron leaves, and it's going to leave a vacancy there that has to be filled. So it's going to pull an electron from somewhere. So it may be another projectile electron that just kind of slips into place there, okay? And if that happens, there's no binding energy attached to this one, right? So the energy of the X-ray photon that's created is the equivalent to the binding energy of the electron that leaves, which was at 69.5. That's kind of like the gravitational pull is holding that into place, 69.5. And if this electron takes its place and it's not bound to anything, then our energy level is going to be 69.5 minus 0 is 69.5 energy X-ray photon. Okay, but it could pull it from somewhere else, and this is kind of where I was going with that, is that if it pulls it from the L shell, it's bound into place with about 12, and if it pulls it from there, then we're going to use the same formula. The electron that left was 69.5, and the electron that takes its place is bound into this shell with 12, right? So that X-ray photon is now going to be 57.5 kVp X-ray photon. You can penetrate a hand all day long with 69.5, or with 57.5. You'd be surprised at what you can penetrate with 57 kVp.
I have a question.
The 0, is that like, so say the electron comes in and takes it out of place,
Mm-hmm.
Can that electron take that place? Is
Can
that what you're
it just
talking about?
snap right back into place? Oh yeah.
And that free one has no...
Yeah, that free one can just go on and do its own thing. Yeah, it absolutely. And not to get, too much into, what used to happen, but in stimulation of old screens and films, that's the theory behind exactly what happened. Is they got excited, jumped out, and jumped right back in. That's what you call fluorescence in imaging screens. So yes, it could just kind of nick it a little bit, knock it out, and it could slam right back into place, and you're still going to get 57.5, or you're still going to get 69.5. Rather.
You've lost me.
I thought that's what you were just.
No, I don't know. I don't even know.
I thought you were saying, could this one be ejected and then fall right back into place?
No, like the one coming in.
Oh.
That one. You know how the electron comes?
Yeah.
The other one. Yeah, the one that hits it. Can that replace it?
Yeah. Yeah. Oh, yeah.
Is that what you're talking about?
Yeah.
When you said you would subtract it. You're 69.5 minus 0.
Yeah. Yeah.
Is that what you
Yeah.
Okay.
Yeah. Exactly. It could grab that one. It could grab the one that knocked it out of place. Yeah. It doesn't matter where it comes from. The determining factor in what your peak energy is going to be, or your energy is going to be based on that X-ray photon is what is it bound to. And in both of those cases, it's not bound to anything. So you're going to get peak 69.5. If it pulls it from somewhere else, you're going to get reduced.
Okay.
Yeah. It's a little.
Whenever Okay, so the characteristics, whenever it pretty much deals with the K shell,
Mm-hmm.
but whenever it's ejecting from the outer shell, is that how you're getting the Compton effect?
Very good question. Okay, all right. So this is truly getting into next semester, and y'all are gonna have a problem separating these two. Okay, so what's going on inside of the X-ray tube is the same thing that's going to be going on inside of the patient. Okay, so Compton is coming from the patient. Okay, so what's happening with Compton is the X-ray photon hits these things and ionizes the tissue. And if it goes, scattered off in a different direction, that's your Compton, okay? So it's the same thing, and this might scare some of y'all a little bit, but you become an X-ray emitter. So you can absorb one X-ray photon and bang around in a bunch of your atoms inside of you, and you can create more X-ray photons that then go on to, ionize more of you. That's why you want to protect yourself, all right? Because you become an X-ray emitter because of the Compton effect. So yes is the short answer, and all at the same time no, because this is target and that's patient.
So Compton is characteristic but inside the patient?
Yeah, essentially.
So where is photoelectric?
Inside of the patient.
Okay.
Yeah,
Compton,
those.
photoelectric.
Yeah, Thompson, classical scattering, all inside of, y'all hadn't talked about it. We'll talk about it next semester. We'll talk about it next semester. But yeah, so with penetration, Thompson, which is classical scattering, Compton scattering, photoelectric effect are all look just like this. We draw it out exactly the same. And the reason I keep saying straight lines, projectile electrons, right? Because when we do this or at least when I do this, for image creation, but before image creation, radiation exposure to the patient, I'm going to do this. Okay? So if I'm drawing a straight line, that's projectile electron, we're talking about target interaction. Squiggly line, you just got exposed. Okay? All right? So all of those, Thompson, Compton, classical is Compton, Thompson, photoelectric, and penetration all refer to radiation exposure inside the patient. Okay.
I think I got it.
All of this is target interaction. This is X-ray creation. That's X-ray exposure to the patient.
Okay, one more question.
Go.
Now I'm confused.
Oh.
So the photoelectric is still the patient, but you're getting a characteristic X-ray?
Potentially, yeah. If you eject an electron, you're going to get a characteristic X-ray. So with you got a lot going on with potential photoelectric. So what does the photoelectric, what does the X-ray photon interact with? Does it hit the nucleus? Does it hit an electron? Has it bounced around a few electrons before it hits one and is eventually totally absorbed? Anytime it ejects an electron inside of your body, you're going to have a secondary photon. If it goes off in some weird direction, it's going to be a Compton. Okay? Okay?
Literally get it out.
Okay. Okay, then I'm going to shut up and stop talking, or I'll confuse you. Anything else?
This will be an easier question.
Okay.
What time is the final on Wednesday?
Oh, good question. Good question. You want to make it 8:30?
No, I don't want to make it at all.
You don't want to make it at all? You remember the,
Yes.
yeah,
Yes.
filtration? Yeah. Okay. All right. Well, if no questions, I'll see you Wednesday. Good luck on your final on Monday.
Friends is just rings out. Friends is rings of the target, right? Characteristics of the target.
Yeah. Yeah.
All right.
It's characteristic of the Compton, but it's on the outer shell to your skin.
Yeah, you're done with clinicals. I'd go